As I indicated in the previous section that there are about 9 to 10 rules for reducing the given block diagram into a single block. As block diagram consists of various summing points, takeoff points and functional description of individual components. Rule 1 was so simple: when the blocks are connected in cascade, how to reduce that blocks in cascade into a single block. Second rule, when the blocks are in parallel, then what will be the resultant. Rule 3, how to eliminate the feedback loop. Any loop, basically it consists of 3 components: summing point, blocks, 2 blocks and 1 takeoff point. So eliminating a feedback loop was rule 3 that we have seen, and rule 4, 5, they were actually takeoff point. When takeoff point is to be shifted ahead of a block or after a block. And then 6 and 7, that shifting of summing point after a block or ahead of a block. So it may look like an additional block is generated while applying the rule, but it is definitely for simplification process only. And rule 8 and 9 also we have seen. All these rules we may not apply for a single block diagram. We may apply 1 or 2 rules, then the block diagram may become very simple. So let us see a couple of examples how to apply these rules for the given complex block diagram and find out the overall transfer function. So you can see this block diagram. I say that it is a complex block diagram. When you see this G2 block and with this feedback here, so the value of H is 1, and this is also the unity feedback control system. Like there is no component or block in the feedback path, so we say that it is a unity feedback. Like when you have G in a forward path, H in the feedback path, then the eliminating this particular feedback loop, we have seen in rule 3 that G by 1 plus or minus GH. Eliminating the feedback loop with G as a forward path gain and H as a feedback path gain, and this is the resultant of eliminating such a feedback loop. Now H value is 1 and H is equal to 1 here, so there will not be any H here, so you have G by 1 plus G or 1 minus G depending on the polarity that is given here. Now suppose you can see that if this point is not there, then happily you can say that this G2 with this unity feedback, you can eliminate this feedback loop by applying rule 3 that G by 1 plus G. So this point is creating the problem. This takeoff point is creating the problem. So I must shift that takeoff point to after a block. So there was a rule we have already discussed, that shifting of this takeoff point to after a block. So let us see now. You can see that the rest of the block diagram you have not changed. It remains same, but only the takeoff point I have shifted to after a block. It becomes like this, and there is a unity feedback anyway with negative sign here. So now you can see that the diagram has become simple because of shifting of this takeoff point to after a block. Now I can happily eliminate this feedback loop whose components are G2, unity feedback and this summing point. So the rest of the block diagram I am not disturbing, but this shift of takeoff point will create some block here, because what is the signal actually going from here, takeoff point to this particular one is before G2, but when I am shifting this takeoff point to after a block, this signal here after G2 is multiplied by G2. If I say that this signal is X, then the signal along this path is Y, that is equal to X times G2. So signal is multiplied by G2 here along this path. So when I am shifting this takeoff point from here to here, the signal was here X, but here it is Gx. So I must use a block of 1 by G2 so that the output should remain same, because the takeoff point output is X here, but when I am shifting this after a block, that the gain available here is multiplied by G2. That's why I am using 1 by G2 so that output should remain same. So in the process of simplification, additional block is generated, but no problem. Still, I will be happy that you can see now this portion. I can eliminate this feedback loop. So what is the resultant of that elimination of this feedback loop is G2 by 1 plus G2, because there is no feedback element, it is unity feedback. Now this G1 remains same. This is the output Y, and this is the summing point you have, and there is a block here. The additional block is created because of shift of takeoff point is 1 by G2 and 1 by G2. Now these two blocks are in cascade, so the product of two individual blocks will be a single block, G1 G2 by 1 plus G2, and in the feedback path there is a block 1 by G2. Now you call that 1 by G2 as H, and that forward path block G1 G2 or G2 G1 by 1 plus G2 as G. Now it is a loop, it is a feedback loop with a negative sign here. So you can eliminate that feedback loop to get the overall transfer function as G by 1 plus GH, where G is this and H is 1 by G2. So you can look at this second example of finding the overall transfer function of given system, which is described by many blocks and then summing points and takeoff points. So how to start? How to get the overall transfer function? My aim is here now, I must get a single block here, overall transfer function, that is C of s by R of s, with this is input and C of s is the output. So I must reduce this entire block diagram into a single block. So you can actually see it is very clear that G1 and H1, it forms a loop, inner feedback loop. So G1 with H1 negative sign, so you can eliminate this as it will become G1 by 1 plus G1 H1. So that is in cascade with G2, so it is G2. Now there is a feedback loop with H2, and you have here G3 and then G4. and this is H3, it is going to another summing point. So the complexity of this particular block diagram is, whenever you apply one rule, you need to draw the block diagram again. When you apply another rule, again you need to draw the block diagram. So that way the number of block diagrams you need to draw, so it looks little laborious, but of course it is required to find out the overall transfer function. So now you can see that we are eliminating this particular feedback loop. This particular feedback loop is to be eliminated, and this resultant will be in cascade with G3. So elimination of this particular feedback loop is rule 3, okay, is a rule 3, and it is G by 1 plus GH formula. It is G by 1 plus GH formula. You call this block as G and this one as H. So this elimination of the feedback loop is G by 1 plus GH. So that is in cascade with G3, so that is multiplied by G3. So once you get this block, then there is a feedback of H3. You need to eliminate that particular feedback loop again by using GH rule, elimination of feedback rule 3. Then once you eliminate, this G4 block comes into cascade to this resultant, and then finally you have only one unity feedback loop that is left over, is this. So elimination of this feedback loop, multiply with the G4, and then that resultant will be the forward path gain with H is equal to 1, and then you can get finally the C of S by R of S. So this is the way you should actually apply the rules, and hardly 2 rules applied, but 2 to 3 times the rules have been applied to determine the overall transfer function. This is another kind of problem. This first diagram, transfer function C of S by R of S, it is very clear that it is a simple single block. It is given by S plus 2 by S plus 1. Now the question here is, these two blocks are said to be equivalent. So this block gain is very clear, but this is not clear. So what should be the value of K, so that the C of S by R of S of this and this will same. Now C of S by R of S of this particular one we need to see. So he says that both are same. If I want to treat both the diagrams are same, then what should be the value of K to have that assumption? The overall gains or transfer functions of both the diagrams must be same, then what should be the value of K? So here you can see that how the blocks are connected here. Not a very complex block diagram, but these two blocks are in cascade. So you get this as K by S plus 1 because it is a product. It is a product. So rule 1 is applied. So these two blocks are in cascade, you get the resultant of K by S plus 1, and this is there anyway. It's a parallel path, but there is no element here, so you can assume that it is 1. So now rule 2, what is that rule 2? When two blocks are in parallel, 2 or 3 blocks are in parallel, the resultant will be the sum. So you can see that this is one path, this is another path, both are in parallel, meeting at summing point, and then so the resultant of this will be 1 plus k by s plus 1. 1 plus k by s plus 1, and this is C of s, this is R of s. So this diagram is simplified into this diagram. Now the overall transfer function of this is 1 plus k by s plus 1, and that is equal to s plus 2 by s plus 1. S plus 1. So you can see that this is s plus 1 plus k is equal to s plus 2 by s plus 1. So what should be the value of k? This is s plus 2 by s plus 1. So the question here is, what should be the value of k so that both the transfer functions are same? So as you see that this is the transfer function of this s plus 2. So I must be, the value of k must be 1. The value of k must be 1 so that the transfer function of both the diagrams is same. So that way the questions will appear that you are applying blocks in cascade, parallel paths, and then you are getting the resultant, comparing with this, and what will be the value of k. So k is equal to 1. The example 4, which we have discussed in the previous section, this comes under reduction of block diagram, and to determine the response C of s for multiple inputs. In this example, there are two inputs given to the system. One is R of s and the other one is U of s. So the question is, what is C of s? What is C of s when both inputs are acting simultaneously? So in this case, we need to determine the transfer function first for each input, then we will combine the responses due to their respective inputs. That is, we need to consider two cases. Case 1 is like U of s ignore and R of s acting alone. R of s acting alone in the system, then what is C of s? So that means we need to determine C of s by R of s in case 1 with U of s 0. And second case, R of s is made 0, R of s is made 0 and U of s is acting now. Then again find out C of s. So for this you need to find out C of s by U of s. So you can find out finally the response when both sources are acting simultaneously, C of s. So let us consider case 1 first with U of s 0, R of s acting alone. So for this case you need to ignore this particular input U of s. So this summing point has no meaning in the circuit. So we can just remove this summing point and then you can add directly the G1 output to the second summing point. So this is the circuit now. As you see this rule 3 of block diagram rules, this is the elimination of feedback loop. So when you eliminate, the resultant of this is G2 by 1 plus G2 H2. it becomes a single block elimination of feedback loop that is in cascade with G1. It is in cascade with G1, and then of course no change in the summing points R of S, and then there is a feedback H1 as it is. Now these two blocks are in cascade, so you will have a single block. It is rule 1. When the blocks are in cascade, the gains are multiplied. So G1 G2 by 1 plus G2 H2 will be the block, and feedback H1 with minus sign. So now you can see that this entire block diagram has become this way now, and again this is a feedback loop. We need to apply rule 3, that eliminating the feedback loop. So R of S is the input, C of S is the output. So you can write C of S by R of S as, you consider this as now G, this as H. So it says G by 1 plus GH, the transfer function of feedback loop. So you can write this way now, G1 G2 by 1 plus G2 H2 by 1 plus G1 G2 by 1 plus G2 H2 into H1. So this is the overall transfer function of this particular diagram has come to this. Now you can simplify this, you will get G1 G2 by 1 plus G2 H2 by, take LCM, G2 H2 plus G1 G2 H1 divided by 1 plus G2 H2. So this gets cancelled. Now what remains, C of S by R of S is G1 G2 by 1 plus G2 H2 plus G1 G2 H1. This is the transfer function for this particular system. But the question is, what is the response due to two inputs? So I can write this as a response C of S, taking R of S to other side, that, so this is the response for this input, R of S multiplied by G1 G2 by 1 plus G2 H2 plus G1 G2 H1. So this is the response when R of S is acting alone in the system. So you just keep this separately here. C of S for case 1, C of S for case 1 is R of S multiplied by G1 G2 by 1 plus G2 H2 plus G1 G2 H1. So this is the response you obtained for R of S ignoring U of S. Now let us go to the second case. So there was a summing point here. There was a summing point here with U of S as input with plus sign. This is also plus. Now what is case 2? Case 2 is R of S is ignored. Made R of S 0 and then consider U of S. So what will happen here, when you make R of S 0, this summing point has got no meaning because no signal, then you can say that summing point has got only one input now. So summing point is meant for addition of 2 or 3 signals. So no R of S here, so summing point has got no meaning. So this H1 can be directly connected to G1. So we can just redraw the system or redraw the circuit, so that now we should find out what is C of S by U of S. So for this I am just redrawing u of s is the input now, then there is another summing point. This is as it is. Now you can see that this feedback through H1 and G1, it is coming to this summing point where u of s is given. So you should have here the product, because H1 and G1 are in cascade. So you can write as G1 H1 with sign plus here, with the sign plus here. So this is the block diagram redrawn with the R of s equal to 0. Yes. Now as usual, this is the feedback loop that can be eliminated by applying rule 3. So it becomes G2 by 1 plus G2 H2, because H2 is a negative feedback. So feedback loop elimination results in single block of that transfer function. So here you have u of s, c of s, and this feedback is not H1 alone. You have seen already here, it is G1 H1. With plus sign, so that is positive feedback. Now you can treat this as G and this as H, so G by 1 minus GH, because there is a plus sign here. So you can write now C of s by u of s is equal to G2 by 1 plus G2 H2 by 1 minus, because it is a positive feedback. So 1 minus G into H. So C of s by u of s, you got this. Now because of a positive feedback, you have got a minus sign here. Now you can simplify this. G2 by 1 plus G2 H2. This will be 1 plus G2 H2 minus G2 G1 H1 by 1 plus G2 H2. So this gets cancelled. Now you get the output C of s is equal to this u of s, you take this side, u of s into, I think you can further simplify this as G2, okay, leave it, G2 by 1 plus G2 H2 minus G1 G2 H1. So this is the response in the case of case 2. This is the response you have got in case 2, and this is the response you have got for case 1. This is the response you have got in case 1. So now what is C of s? When both the sources are acting simultaneously, you need to add them. Okay. So C of s, case 1 and case 2, you must add. So the response will be C of s is equal to R of s into that block G1 G2 by 1 plus G2 H2 plus G1 G2 H1 plus u of s, this term you need to put G2 by 1 plus G2 H2 minus G1 G2 H1. So we have not applied any complex rules here. It's only elimination of feedback loop and blocks in cascade. So only first 3 rules hardly we have applied to find out the response of a system when both the sources are acting simultaneously. This is the way we should find out the transfer function or response when multiple inputs are given. So this is another example of finding the transfer function for a given block diagram. So the question is here again, what is C by R? What is C by R? You can actually see here, now there is a signal that actually R is applied to G1 and then it goes in this way. The same signal R is being applied to this summing point and also to this summing point. So I can redraw this figure to understand better. You can see that the signal that is actually going, there is no component here, there is no additional block, so the value can be taken as 1. So this also 1. So the resultant of these two is 1 plus G1, 1 plus G1, and there is a block anyway G2, and there is a summing point C, and this is R, and this is signal R is going to this summing point also. Now it is simplified like this, because the same signal R is going to both the summing points. So I have added this 1 plus G1 because these two are in parallel. Rule 2 says 1 and G1 are in parallel up to this summing point. So I can get a single block, G2 as it is, and then this signal again is added here 1. So now these two blocks are in cascade. These two blocks are in cascade. So you get as G2 into 1 plus G1, and then C, and this signal is going to the summing point 1 with the same sign, plus and plus. Now you can see that between input and output there are two paths in parallel. So this block is in parallel with 1. So it is simply sum. It is simply sum 1 plus G2 into 1 plus G1 is the block gain. So this is the way you should find the transfer function. Now C by R is equal to 1 plus G2 plus G1 G2. This is the overall transfer function of this particular example. We have seen 4 to 5 examples of reduction of block diagram applying rules which we have discussed today, but still you need to practice good number of problems on block diagram reduction to get perfection. And in the next topic is signal flow graph. Signal flow graph is to be discussed. It is an alternate version of the block diagram. We have seen in the block diagram it is very complex. When you are applying one rule, then you may have to draw the entire block diagram again, and it is very laborious, time consuming, and not that easy to get overall transfer function. So we will discuss the signal flow graph approach invented by Mason, scientist, and he has developed the formula called Mason's gain formula that is applied to find out the overall transfer function of a given system for a signal flow graph. It is a graphical representation of a system.